All right, so welcome to the third set of notes on electric circuits. This is all going to be about something called Kirchhoff's laws. So we've all already seen that we can connect our circuits in two ways. So we can either connect them in series or in parallel. And what we started to notice is that when we connect these two circuits in these different ways, that it changes how those circuits behave. So you can see, for example, on the left here, I've got a series circuit with two light bulbs, and on the right, a parallel circuit with two light bulbs. Now notice that the battery in each case is a 9-volt battery, and each of the light bulbs in each case are both 10 ohm resistors. But it's really clear from what's going on here that their behavior is different. The series light bulbs are a lot dimmer than the parallel light bulbs, and so on. So we're going to take a look at what causes these differences. So the big difference is in the resistance, or the total resistance of the circuits, whether you attach in series or parallel. So the first thing I want to look at is currents. Okay, what happens to the current in both a series and compare that to parallel? So if we look at our series circuit, what we'll notice right off the bat is that there's only one pathway for the electrons to flow. And so no matter where we measure our current, whether we measure it here at the battery or right next to one of the light bulbs, the current's going to have the same value in every location. And so what we say is that the total current is just equal to the current through the first resistor, which is equal to the current through the second resistor, which is equal to the current through the third resistor, and so on. No matter how many resistors or light bulbs or things you have in your circuit, if they're connected in series, the current through each of them is going to be the same. Now, if you contrast that with what's going on in the parallel circuit, you can see here that the total current through the battery is giving us 1.8 amps, and yet through this branch right here, I get 0.9 amps, and the same thing through this second branch. What you'll notice right away is that these two currents add up to this total, which sort of makes sense, because if you think of the current like a river flowing, a certain amount of water flows out of this junction, and some might go through here and some might go through there, but eventually it has to all meet up again, and when it meets up, it's going to add up to that total. And so what we say for a parallel circuit is the total current is equal to the current through the first item plus the current through the second plus the current through the third, and so on, up to however many things we have connected in this circuit. So Kirchhoff's current law can be just generally stated that the sum of the currents entering a junction must equal the sum of currents leaving that same junction. And this is just another way of saying, essentially, that charges aren't going to disappear. Electrons aren't just going to magically disappear into a puff of smoke. They're going to just keep on moving through the circuit, and they may split apart, but they're going to come back together at a later point. So let's look at voltage. Now we think about there's Kirchhoff laws for voltage, and the way we state this is the sum of the potential differences in a circuit must add up to 0. So that is to say, when we look at all the total ramps up and then drops in voltage, those have to add up to 0. And that's just another way of restating the law of conservation of energy. Right? This is just saying that as a battery or some sort of voltage source pumps up the electrons full of energy, those electrons are going to use that energy somewhere along the circuit, in a light bulb, in a resistor, wherever. So you'll remember that when we have a battery, that the potential difference increases across the terminals of the battery, and then that potential decreases across a load. And the load is just the general term for resistor or light bulb or anything that uses that energy, motor, anything like that. So essentially these increases and drops must add up to 0. And if we go back to our series circuit, what we'll notice is that this 9-volt battery, if I measure the voltage across each of the light bulbs, I'll notice that each light bulb basically uses up half of that, 4.5 volts per light bulb. So I'm going to get 9 volts of juice out of this battery, and these electrons are going to use some of it on the first light bulb and some of it on the second. And in this case, it's going to be equal amounts because they happen to be identical light bulbs. So for a series circuit, the total voltage would equal V1 plus V2 plus V3, and so on. Now, since there's only one path for each electron's across the circuit, all of those voltage drops, when you add them up, will add up to be the same as the total. Now for a parallel circuit, it's a little bit different. Now, this is a little bit strange. Take a look at this circuit here. I notice that this battery over on this side is giving me 9 volts. But the funny thing is when I measure the voltage drop across each of these light bulbs, I also get 9 volts. And while this may seem strange at first, what we need to remember is that the electrons are going through one path or the other. These electrons aren't going to go through both of these light bulbs. So if they come out of this battery with 9 volts of potential, then they're going to have to use all 9 volts just on this light bulb or just on this one. And so our rule for parallel circuits is that the total voltage is equal to V1, which is equal to V2, which is equal to V3, and so on. Which is to say, when you have different loads in parallel, each one is going to receive identical amount of voltage. Okay, so note the potential difference is the same across each load in parallel. Okay, so Kirchhoff doesn't exactly have rules for measuring resistance, but we can kind of just reason out what those rules might be. And so if we were to look at, say, back to our series circuit, what we'll notice is that these electrons, they have to fight their way through the first resistor or light bulb, and then they have to fight their way through the second. We could do a calculation using Ohm's law and note that 9 volts is giving us a total current of 0.45 amps. So really that works out to be 20 ohms worth of resistance. And no big surprise, each of these individual light bulbs are giving us 10 ohms apiece. And so in series, the total resistance is equal to R1 plus R2 plus R3, and so on. And so the total resistance in a series circuit is the sum of the individual resistors, or resistors. So since each electron has to push its way through each resistor, then it sort of makes sense that these things add up. Now where things get a little bit confusing is when we look again at parallel circuits. So let's jump back to our circuit here. I'm using 9 volts of potential, and if I look at my total current, I'm getting 1.8 amps. If I do the math on that one, the total resistance of my circuit is actually 5 ohms. Even though the individual light bulbs have a resistance of 10 ohms, the total resistance of the circuit is less. In fact, it's half of the total of each of those. And so we're not going to go through the derivation of where this comes from, but to calculate the total resistance, we have to actually use this inverse. And so we say 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. And so whenever we add resistors in parallel, the total resistance actually has to decrease. And this is a little bit strange because this can even happen even if the second pathway has a higher resistance than the first. Just the fact that we're adding more potential pathways is going to lower the overall resistance of our whole circuit. So let's do a quick recap of all the rules here so we can commit them. Because the problem with this is that they're really very similar, and so it's really, really easy to mix them up. So let's look at voltage first. In series, the voltage total is going to be the sum of the individual voltages. Whereas in parallel, the total voltage is going to be equal to the voltage across each individual load in parallel. With current, the total current in a series circuit is going to be equal to the current through the first item, or the second, or the third. The current has to be the same everywhere. Whereas in parallel, because we have pathways splitting apart, the total current is going to be equal to the sum of the individual currents through each of those separate junctions. And the total resistance when we're in series is going to be the sum of the individual resistances. Whereas in parallel, we have to use this inverse function for finding the total. 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, and so on. All right, that's it for Kirchhoff's laws. You're all done.